Hello, we are now in week 5 of this course, analog circuits, and in the past week we had covered the modules on gain margin and phase margin. So we saw that gain margin is a measure of how stable a system is. Higher the gain margin, the more stable the system is. Similarly, phase margin is also a measure of how stable the system is. Higher the phase margin, the more stable the system. So ideally, I also mentioned in the last module that the phase margin should be somewhere between 45 degrees to 180 degrees. Now in this module we will be covering an example of a typical analog circuits and see how depending on the feedback the amplifier or the system, the analog circuit, will be in the stable region or in the unstable region. So let us recollect once again. Gain margin, so gain margin, I will just once again just repeat this figure. So this is theta, this is mod A beta. This is the point where your magnitude of AB becomes equal to 1. So this is on a log scale, this will be 0. So this is say corresponding to theta, and this is minus 180 degree corresponds to the frequency. So this is my omega 180 and this is omega 0 dB. Okay. So here what we see is that this is my phase margin, and this is my gain margin. Now an alternate way of representing this magnitude of A beta equal to 1 could be this. So we know a potentially unstable situation arises when my magnitude A beta is equal to 1. Now here I have many times said that this beta is frequency independent. So I can write this equation alternatively like this. Then if beta is frequency independent, it is just a scalar quantity, then for at the point of potential instability, not that the system is unstable yet, but if this condition is satisfied, that is magnitude A beta equal to 1, which alternatively is written as magnitude A equal to 1 upon beta, then it is a case of potential instability. That is, there is now, it is no longer unconditionally stable, there is a possibility that the system can become unstable. So then instead of measuring, so if I have a plot like this, then say this is my magnitude of A plot, okay, this is in dB, and this represents my 1 upon beta. Then can I write that instead of, so can I represent my omega 0 dB point as that frequency where these two intersect. So this is my omega 0 dB. Okay. So this kind of representation now gives us an easy way of analyzing various systems. So here what we have done is we have separated the open loop magnitude, the magnitude of the open loop transfer function from the feedback network, from the gain provided by the feedback network, and this way now. So, irrespective of what my feedback network is, this line, this solid line remains the same, but depending on what my feedback factor is, this dotted line will change. For example, if I change my beta, make it lesser, then this line will shift downwards. Okay. So, now with this in mind, and so in that case when it shifts downward, my omega 0 dB will shift here. Okay. So, now with this in mind, let us see a system with the transfer function given as follows, like this: a of j f, here I have replaced omega with f upon there are 3 poles, one at 10 raised to 5, another at 10 raised to 6, and another at 10 raised to 7. So, if I draw the Bode plots for this particular transfer function, this mind you is the open loop transfer function. So, the Bode plot will be something like this. So, this is my magnitude plot, the top half, and this is my phase plot. So, I can maybe label it as this is my and this is in log scale. So, this is log of f rather, log of, so this is log of f. Now, first consider the case when suppose my 1 upon beta line passes through this point. So, this is my log of 1 upon beta line. Now, here this log of 1 upon beta crosses, so this green line which represents log of 1 upon beta crosses the red line which represents log of A or A in dB. So, this is actually 20 log of 1 upon beta at the frequency f180. So, f180 is the frequency where the phase of the transfer function becomes equal to 180 degree. So, at that frequency itself, the contribution of the feedback network represented by this 20 log of 1 upon beta. So, at that frequency itself it crosses the red line. So, what does that mean? It means that the feedback is such, first of all, that there is 0 phase margin, okay. And note that in this region where this green line crosses the red line here, the slope is minus 40 dB per decade. Okay. Here the slope is minus 20 dB per decade, and here it is minus 60 dB per decade. Now, from the discussions that we had in the last lecture, we know that this minus 20 dB per decade corresponds to the region where only a single, or there is the contribution of only a single pole. If the contribution of this feedback network represented by this green line passes through this region, this minus 20 dB per decade region, then the system will be unconditionally stable. So, for example, suppose here this is also 20 log of 1 upon beta. So, suppose the feedback network is adjusted so that this green line shifts from here to here, and here as you can see the phase is minus 108 degree corresponding to this frequency, then the system will be unconditionally stable. The system will be unconditionally stable because even though the magnitude A beta is becoming equal to 1, but the phase, but because the feedback network line passes through the minus 20 dB per decade region, the phase will never exceed minus 180 degree. Hence, if we have our feedback network such that it passes through the minus 20 dB per decade region, then we can say that the closed loop system will continue to be unconditionally stable. Once again I will repeat, if we ensure that a feedback, a negative feedback system such that the contribution of the feedback network, this 20 log of 1 upon beta line, passes through the minus 20 dB per decade region, then the closed loop system, this minus 20 dB region, mind you, is that of the open loop transfer function. But if this green line passes through the minus 20 dB per decade region, then we can guarantee that the closed loop system will also be stable. Why? Because even though the magnitude A beta equal to 1 at this frequency, because the feedback line is passing through the minus 20 dB per decade region, the phase will never exceed 180 degree. Since the phase can never exceed 180 degree, the system will continue to be stable. However, that is not the case here. When your feedback network is such that it is passing through the minus 40 dB per decade region, there is a possibility that the phase can exceed minus 180 degree, and hence the system can become unstable. Similarly is the case if the feedback network line runs through the minus 60 dB per decade region. So, then our goal of any feedback circuit design should be that this feedback network should pass through, preferably through the minus 20 dB per decade region. Okay. If we want our closed loop system to be unconditionally stable, then it should pass through the minus 20 dB per decade region. Fine. Okay. The other thing is, so then why do not we do that always, isn't it? If that is the conclusion, then why not we always have our feedback network pass through the minus 20 dB per decade region. Now, note that when you are passing your feedback line through the minus 20 dB per decade region, your bandwidth is decreasing. This is the frequency at which your 0 dB loop gain is being obtained. Hence, the bandwidth of the system is much lesser as compared to the case when the feedback line is passing through the minus 40 dB or minus 60 dB per year, isn't it? Here, this is the unity gain bandwidth, this region from here to here. In this case, the unity gain bandwidth is from here to here. So, that is one disadvantage. To make the system more stable, we have to compromise on the bandwidth. So, that is one problem of this system. Now, coming back to the circuit, this red line, this lower red line represents the phase response, and we see that this minus 180 degree phase is obtained only when we are passing through the minus 40 dB per decade region. This tallies with the discussion we had in the last module, where we said that this minus 40 dB per decade region corresponds to the two pole case, that is the region where the impact of two poles is there, and therefore, the minus 40 dB per decade region is a potentially unstable region for the feedback line to pass through. And as we see in this case, when this green line passes through this minus 40 dB per decade region, the phase is indeed exceeding minus 180 degree. If it had been a little lower, then here it is same as my 180 degree. Had this line been a little lower, then the phase would have exceeded 180 degree. So, in conclusion, we see that for stable closed loop system, it is for a stable closed loop system to be unconditionally stable, it is necessary that the feedback line passes through the minus 20 dB per decade region. In the next module, we shall see how for a system where such a thing does not happen, still we can achieve the stability by what we know by a technique which we refer to as frequency compensation. So, that is what we will cover in the next module. Thank you.